can be thought of as coming from the idea that you can actually separate out numbers. So I can call 64 4 times 16 and actually find out the square root of each bit separately and multiply them together and get the same answer, but plus or minus 8 either way. And so we use that. Another example might be the square root of 20 can be split into the square root of 4 times the square root of 5, and that sometimes means we can do this bit of it, because that's 2, and leave this bit, which is a bit of an awkward number, and that can be useful sometimes. And this complex number idea comes from this idea exactly. If I look at a number like this, the square root of minus 64, you can't do it, because whenever you square a number, in other words, that means multiply it by itself. When you multiply it by itself, in other words, it's always going to be positive. So if you put this into a calculator, you get math error. But you can get around it. And this is what the ancient mathematicians did to get around this problem. And so they could carry on and actually solve quadratic equations, because when you end up with a square root, that's where it arose actually. Solving these things called quadratic equations, you know from that formula that we've been looking at, as part of that formula, you have the square root of b squared minus 4ac. You might remember it, okay, as part of solving a quadratic. If this root is negative, you grind to a halt because you can't go any further. And so this is an attempt to try, it was initially an attempt to try and carry on and solve these quadratics by calling the square root of minus 64 the square root of minus 1 times 64. Because I can do the square root of 64, that's plus or minus 8, leaving this square root of minus 1. And that always is the one you can't do. You can always reduce it to a positive bit, the 64, and the square root of minus 1. So this square root of minus 1 is what's called the imaginary number. Mathematicians tend to use the symbol I, engineers tend to use the symbol J to represent imaginary numbers. So therefore, we say the square root of minus 64 equals plus or minus 8j. And that's how we'd write it. You can sometimes, you'll see it in some textbooks as written, and in fact some of the lecturers in the college, the math, I know Mike Betts does for a start off, because I team teach with him on some of the courses, tends to put the J first, and that's common. But algebraically that doesn't look right to me, so I always put the J afterwards. But you'll see it written before or afterwards. Doesn't matter where it is, it's the imaginary number. Yeah. So this is an imaginary number. The whole thing is an imaginary number.
You always have to put the plus and negative. It's the two numbers.
Not always, no. Sometimes, as we'll see, it's positive or negative, but as far as we can go at the moment, it could be positive or negative. But yeah, it's not always both. Okay. Right. So let's pause there. So the complex number has got two parts to it, and as we'll see, that's what makes it useful to engineers. It's got a real part and an imaginary part. If we look at this example, and again, hopefully you recognize that as a quadratic, and we're solving it using that quadratic formula, and x, the value we're after, turns out to be, so this x turns out to be minus 4, so do you remember the formula, minus b plus or minus the square root of b squared minus 4ac all over 2a, blah, blah, blah. We end up with x equals minus 4 plus or minus root minus 8, a negative root, all over 2. So we can actually go on now and solve it, because before we'd have to stop and say no solution because that's negative. So we can't solve it, but now we can, because we know that this is we can use the imaginary number idea here. And so we can say x equals minus 4 plus or minus, oh actually let's make it a little bit more straightforward. Sorry, why did I use that? Let's use one that's easy to root, minus 9. Okay, perhaps you could change that to a 9. Plus or minus, what's the square root of minus 9 now, using our imaginary numbers? Yep. Right, so it's plus or minus 3 times the square root of minus 1, which is j. Right, Josh? All over 2, which equals minus 4 over 2 plus or minus 3j over 2. We can split it, which gives us, what's minus 4 over 2? That's minus 2 plus or minus 1.5j, and that's our answer. So we've got two solutions, minus 2 plus 1.5j and minus 2 minus 1.5j. So we've got these two answers, and we put them in a bracket. So, Josh, you were saying, is it always plus or minus? Well, there's our possibles. And we might decide it's going to be that answer we're interested in or the bottom one. So we use one or the other often, not both. So, for example, minus 2 plus 1.5j comes from that. So, complex number comes from the solution of a quadratic, often, and there are other situations it can arise, but this is the most common. And you end up with this. Minus 2 plus 1.5j is an example of a complex number. So there it is. That's a complex number. And the complex number has a real part and an imaginary part. That's what makes it complex. It's got two parts to it, a real part and an imaginary part. So not complex in the sense that it's complicated, but complex in the sense it's made up of two bits, a real bit and an imaginary bit. The use of complex numbers comes from using these two bits or these two parts to represent quantities, vectors in two dimensions. Because we've got two parts, we can use two dimensions to represent it, and I'll show you what I mean. So in other words, we can represent a vector that's got an x and a y coordinate associated with it. So we can start talking about things that have a direction associated with them, vectors in other words, using these complex numbers. So how can we represent things in two dimensions? We have two coordinate systems that we use that we can use with complex numbers. One is the polar coordinate system, and one is the rectangular or Cartesian coordinate system. We've used these before. The rectangular coordinate system is like if I want to measure the position of the end of this vector, say that point there, I give a coordinate. I go so far along the x-axis and then so far up the y-axis, and there it is. So that would have a coordinate, xy coordinate. And in this case, it might be something like minus 3 and up 2, something like that. Okay. We can also use the polar coordinate system to represent the position of this point, i.e. this vector here. We can represent that point by an angle that we've turned round through anti-clockwise. Remember, we go anti-clockwise from this real positive x-axis. and a distance. And this is the sort of coordinate system that's used in maritime, in finding the position. You measure a position from north and then a distance. Here we're measuring a position from the angle from the x-axis, and then a distance, r to the end. And so we'd represent that by the coordinate system r theta, angle r theta would represent the position of the point. So we've got the polar and the rectangular coordinate systems, and we can use those to represent complex numbers, because what we do is we call this axis always the real axis. So the horizontal axis, the x-axis, is called the real axis, and on there we put the real numbers. Up here is the imaginary axis, always. So the vertical axis is always the imaginary axis. So I can represent a complex number like the one we've just been looking at, or let's take another example, 3 plus 2j as going, or minus 3 plus 2j as going, minus 3, whoops, minus 3 along the real axis, and up to along the imaginary axis. So this vector here represents that complex number. And we can also represent it in terms of an angle and a distance. So we need to be able to convert from this form to the polar form. So we say this complex number is in rectangular form. What is it in polar? We can do that on the calculator. That's dead easy. Okay? If you get your calculator out, okay. So looking at this calculator, if you look at the plus and minus buttons, bottom right, you'll see above the plus button it says POL, polar, and above the minus button it says RAC for rectangular. The one that you're interested in is the one for the coordinate system you're going to. So I'm converting from rectangular to polar. So the polar button is the one I press. So I hit shift and then the plus button, and that gives me the polar coordinates. Now it's asking for the coordinates. X first, so minus 3. So you hit the minus sign and then 3. The minus sign in the bracket top left, not the minus sign next to the plus button. Okay. And then it's after a comma for the coordinate system. And if you look above the closed bracket symbol, it says comma there. So you hit shift and then close bracket, and that puts a comma in. And then you put in the 2. You don't put the j in. And then close the bracket, equals. And I get 3.6. You do close the bracket. Actually, you can get away without closing it often. 3.6, and then if you scroll along, you'll get the angle. So, yeah, it's 3.6. Yeah. Yes, it is, yeah. That's right. Angle 146. Whoops. Yeah. So in summary, I can write complex numbers either in rectangular form, so that's, if you see a number looking like this, minus 3 plus 2j, for example, you know that's in rectangular form. And this is the real bit of the number, which goes on the x-axis, and this is the imaginary bit, which goes, yeah. So this is always on the x-axis, and this is always on the y-axis. This is the same complex number, so we can write a complex number in 2 forms, but this is in polar form. And here This is called the modulus and this, for some weird reason I've never really understood, is called the argument. Yeah. The angle is often called the argument. When you talk about these things in electronics, which you will do, that would be actually the phase angle or the angle. So we don't use the term argument, but in mathematical terms that's called the argument. And this is basically the magnitude so that's the size of it, the distance or how far it's traveled, or the size of the force if you're using it to represent forces, as we'll see, and this is the angle from the x-axis. So we can use autograph to represent vectors in polar or Cartesian coordinates. So as far as autograph is concerned, all you're doing is showing a coordinate on the x or y axis, Cartesian or rectangular coordinates, or a distance and an angle if we're using polar coordinates. So we've got two coordinate systems that we use. One is the rectangular coordinate system, and if you look at the screen, you can see, if I hover over this button, that's the Cartesian grid, Cartesian rectangular coordinates. The one next to it is the polar grid. So if I click on the polar grid, instead of getting a whole series of squares where I'm going to go along x and up y, what this is representing is I'm going a distance. So these are the distances. This is the modulus, so size of the vector is 1, 2, 3, 4 and so on, and then you go round an angle. So this is the polar coordinate system. So the circles represent a distance from the origin. So if we go back to the Cartesian coordinate system again, and I want to put a vector into here, say the one we've just been looking at, minus 3, 2, what I do is I right click. We'll be doing this in a second, so listen in. You right click anywhere on the screen, doesn't matter, and it asks you to enter coordinates. And by default, the coordinate will be at the origin, which is exactly where I want it to be, because that's the start point of my vector. So I hit OK, and then it puts a coordinate in the middle. So that's my vector start point. What I then do is right click there and add a vector. And then asks for the coordinates. I'm going along the x-axis and going minus 2. So what goes in there is minus 2. And then the y-coordinate is 3. Is it? Oh yeah, thank you. Minus 3, 2. Hit OK, and it will draw in that vector, which in this situation that's representing the complex number minus 3, 2. If I want to do it on the polar coordinate system, so let's close this. You could do, but in your assignment I'm going to ask you to draw out some complex numbers, and I'm hoping you can use autograph to do it. So the polar coordinate system, now if I'm in a polar, again right click in the middle, enter coordinates, 0, 0, that's where I want it, in the middle, right click and enter a vector, and now we're looking for the r and the theta. Note theta, pi over 4, that's in radians. So I want to make sure I'm in the correct thing here, and I've got the choice to measure my angles in radians or degrees. So check degrees, right click again in the center, into the vector. So now it's given me the option to give it in degrees. So what was the modulus? 3.6. And the angle? 146. Hit OK. And again it draws a vector. Okay. which should match exactly with the one we've just done because it's the same vector in. But what I want you to do now then is just log on and try putting those two vectors onto autograph. So now as a little exercise, look at those four complex numbers. I've given you two in rectangular and two in polar. I want you to convert them with your calculator to the other system. So convert that to polar, that to rectangular, that to polar, and that to rectangular. And then draw each of those on autograph and see that you get the same vector both ways, that they look the same.